This is SpaceTime Series 27, Episode 98, for broadcast on the 14th of August 2024. Coming up on SpaceTime, a hidden ocean on Uranus's moon Ariel, the Webb Space Telescope sees the birth of stars in a new light, and what happens to the remains of a neutron star merger. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
There's growing speculation that Uranus's moon Ariel could harbour a hidden subsurface ocean under its frozen crust. Ariel's surface is coated with a significant amount of carbon dioxide ice, especially on its trailing hemisphere, which always faces away from the moon's direction of orbital motion. Now, this fact presents somewhat of a surprise, because even at the frigid reaches of the Uranian system, some 20 times further away from the Sun than the Earth, carbon dioxide readily turns into a gas and is lost into space. Now, scientists have long theorized that something is supplying fresh carbon dioxide to Ariel's surface. One hypothesis suggests that interactions between the moon's surface and charged particles in Uranus's magnetosphere are creating carbon dioxide through a process called radiolysis, in which molecules are broken down by ionizing radiation. But a new study reported in the astrophysical journal Letters suggests a different idea, namely that carbon dioxide and other molecules are emerging from inside Ariel, possibly even from a subsurface liquid ocean. The authors used NASA's James Webb Space Telescope to collect chemical spectra on the moon and then compared those results with spectra from simulated chemical mixtures in the lab. They discovered that Ariel actually has some of the most carbon dioxide-rich deposits in the solar system, adding up to an estimated 10 millimeters or more in thickness on the moon's trailing hemisphere. Now, among those deposits was another puzzling find, the first clear signals of carbon monoxide. The study's lead author, Richard Cartwright from the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, says that carbon monoxide simply shouldn't be there. He points out that temperatures need to get as low as 30 Kelvin, that's minus 243 degrees Celsius, before carbon monoxide is stable. And Ariel's surface temperature averages around 18 degrees Celsius warmer than that. It means the carbon monoxide there would have to be actively replenished. Now, radiolysis could still be responsible for some of that replenishment. But the lab's experiments have shown that radiation bombardment of water ice mixed with carbon-rich material could produce both carbon dioxide and carbon monoxide. Thus, radiolysis can provide a restocking source and account for the rich abundance of both molecules on Ariel's trailing hemisphere. But many questions remain about the Uranian magnetosphere and the extent of its interactions with the planet's moons. Even during the Voyager 2's flyby of Uranus nearly 40 years ago, scientists suspected that such interactions would be limited because Uranus's magnetic field axis and the orbital plane of its moons are offset from each other by about 58 degrees. So instead, the bulk of the carbon oxides may be coming from chemical processes that happened, and possibly are still happening, in the ocean waters beneath Ariel's icy surface, escaping either through cracks in the moon's frozen crust or possibly even through eruptive plumes. What's more, the new spectral observations by Webb are hinting that Ariel's surface may also harbour carbonate minerals, salts, that could only have come through the interaction of liquid water with rocks. Cartwright says that if his interpretation of the carbonate feature is correct, that means it had to form in the moon's interior, and that's something astronomers absolutely need to confirm. Astronomers have already suspected that Ariel may be geologically active because its surface is covered in gash-like canyons, crisscrossing grooves, and smooth spots thought to be formed from cryovolcanic overflows. A study last year by Johns Hopkins Applied Physics Laboratory scientist Ian Cohen even suggested that Ariel and or its sister moon Miranda could be emitting material into Uranus's magnetosphere, including possibly through plumes. Cohen says all these new insights are underscoring how compelling the Uranian system is. Whether it's to unlock the keys of how the solar system formed, to better understand the planet's complex magnetosphere, or to determine whether these moons are potential ocean worlds, many scientists are now calling for a future mission to explore Uranus. Last year, the planetary science community prioritised the first dedicated mission to Uranus, raising hopes that a scientific voyage to the turquoise ice giant could be on the horizon. Cartwright sees this as an opportunity to collect valuable data about the solar system's ice giants, Uranus and Neptune, and their potentially ocean-bearing moons. But it would also be a chance to finally receive concrete answers that are only possible by actually being in the system. For example, most of Ariel's observed grooves, suspected of being openings to its interior, are on the trailing side of the moon. The trouble is, astronomers really haven't seen all that much of this tiny moon's surface. Voyager 2 only captured about 35% of Ariel's surface during its brief flyby. Scientists simply aren't going to find out much more until a dedicated science mission can be undertaken. This is SpaceTime. Still to come, the James Webb Space Telescope sees the birth of stars in a new light. And what happens to the remains of neutron stars when they merge? All that and more still to come on SpaceTime. NASA's James Webb Space Telescope has captured the historic first direct images of a key phase of how newborn stars are actually formed. The new observations, reported in the Astrophysical Journal, have long been sought after by astronomers as they show an important process in stellar evolution. The images, captured by Webb's near-infrared camera, show details of a young nearby star-forming region in the Serpens Nebula, an especially dense cluster of newly forming stars only around 100,000 years old, which is located some 1,300 light-years away. Now, some of these stars will eventually grow to be as massive as our Sun. Astronomers found an intriguing group of protostellar outflows formed when jets of gas spewing out from nearby stars collide with nearby gas and dust at high speeds. Now, typically these outflows have varied orientations within one region. However, here they're all slanted in the same direction, to the same degree, sort of like sleet falling during a snowstorm. The discovery of these aligned objects provides new information into the fundamentals of how stars are born. Astronomers have long assumed that as clouds collapse to form stars, these stars will tend to spin in the same direction. The trouble is, this has never actually been directly seen before. That's where the new images come in. They're showing a series of aligned, elongated structures, an historical record, if you will, of the fundamental way in which the stars are born. Now, as an interstellar gas cloud collapses in on itself to form a star, it spins up. In other words, it tends to spin more rapidly. That's called the conservation of angular momentum. It's the same way an ice skater spins more rapidly when they bring their arms in close to their body. Now, the only way for that gas to continue moving inwards is for some of that angular momentum to be removed. A disk of material forms around the young star to transport material down, like a whirlpool around a drain. The swirling magnetic fields in the inner disk launch some of that material away in twin jets. They shoot outwards in opposite directions, perpendicular to the disk of material. Now, in the new Webb images, these jets are signified by bright, clumpy red streaks of shock waves from the jets hitting the surrounding gas and dust. The study's lead author, Joel Green from the Space Telescope Science Institute in Baltimore, Maryland, says Webb has allowed astronomers to catch these extremely young stars and their outflows, some of which previously appeared as just blobs or were completely invisible in optical wavelength images because of the thick dust surrounding them. Astronomers say there are a few forces that potentially can shift the direction of these outflows during this period in a young star's life. But one way is when binary stars spin around each other and wobble in orientation, twisting the direction of the outflows over time. The study's authors will now use Webb's near-infrared spectrograph to further investigate the chemical makeup of this cloud. Astronomers are interested in determining how volatile chemicals survive star and planet formation. Volatiles are compounds that sublimate or transition from a solid directly into a gas at relatively low temperatures, and that includes both water and carbon monoxide. They'll then compare their findings to amounts found in protoplanetary disks of other similar type stars. The majority of our water here on Earth originated when the Sun was an infant protostar billions of years ago. Looking at the abundance of these critical compounds in protostars just before their protoplanetary disks are formed could help scientists better understand how unique the circumstances were when our own solar system was formed. This report from NASA TV.
Situated only 1,300 light-years from Earth, the Serpens main region covers a span of 16 trillion miles by 11 trillion miles. Its proximity to Earth makes it an ideal region for studying individual young stellar objects. Serpens is a famous stellar nursery. It has been imaged before, but this is the first time we've had an instrument that can give us this level of detail. A groundbreaking discovery has been made by NASA's James Webb Space Telescope in the Serpens Nebula. Astronomers observed aligned protostellar outflows within this region for the first time, providing unparalleled insights into star formation theories. These protostellar outflows occur when jets of gas expelled by newborn stars interact with the surrounding gas and dust. What sets this discovery apart is that the outflows are aligned in the same direction. The remarkable alignment of these outflows illustrates previously unseen details of how stars are born. As we continue to explore this new image, we find multiple captivating features that also warrant a closer look. We orient ourselves by looking for the Bat Shadow, a large shadow of a planet-forming disk recently imaged by Hubble. To the right of the Bat Shadow lies an eye-shaped feature, which appears as if a star is bursting through. Astronomers say looks may be deceiving here. Despite its resemblance to a void, it may simply be a result of layered gases with varying densities, akin to the phenomenon observed in the renowned Pillars of Creation. To the right of this is an extremely dark patch, which could be a similar occurrence of layered gases and dust. No near-infrared light is able to get through because this area is so dense in comparison to the rest of the region. This region is also home to some particularly eye-catching stars. SMM1 is a binary protostar, two protostars that form together, orbit each other, and produce two separate but overlapping outflows. OO Serpentis is a young star still surrounded by a lot of gas and dust that hasn't started the main phase of its life yet. It erupted in 1995. It's rare for astronomers to capture this extreme type of violent outburst because it doesn't last very long. With this new image of the Serpens Nebula, Webb provides one of the most complete pictures of star formation astronomers have ever seen.
This is SpaceTime. Still to come, what happens to the remains of a neutron star when they merge, and later in the science report, a new study claims that thinking too hard really does make your brain hurt. All that and more still to come on SpaceTime. Scientists are resorting to some of the world's most advanced supercomputers to try and figure out how quickly a stellar mass black hole is likely to form from the merger of a pair of neutron stars. Black holes are the densest objects in the universe, containing infinite density in zero volume. The gravitational pull is so strong that any material that falls beyond a point of no return called the event horizon will continue falling forever into the black hole singularity, and nothing, not even light, can escape. Because the laws of physics break down inside black holes, understanding them is extremely difficult. Even their immediate neighbourhood is difficult to comprehend. The trouble is, neutron stars really aren't all that much less mysterious. Just like stellar mass black holes, neutron stars can be formed either by the death of a massive star in a core collapse supernova explosion or through the merger of two less massive stars. In the aftermath of a collision of two neutron stars, a new celestial object, which astronomers are calling a remnant, emerges, shrouded in mystery. Scientists are still unravelling its secrets, including whether it collapses directly to form a black hole or whether other things happen first, and also how quickly all this takes place. Now, scientists from Pennsylvania State University have used supercomputer simulations with general relativistic neutrino radiation hydrodynamics to try and better understand the internal structures of these neutron star merger remnants. They also looked at how the remnants are likely to cool down by emitting neutrinos. By observing when neutron stars merge in space, scientists are gaining insights into how nuclear matter behaves, how it acts under extreme conditions that simply can't be replicated here on Earth. Nuclear matter is a hypothetical substance made up of protons and neutrons held together by the strong nuclear force. Of special interest to scientists is whether the pressure from the strong nuclear force can stop black holes from forming. To try and get the answers, the authors used the computational resources available through the United States Department of Energy's National Energy Research Scientific Computing Center, the Leibniz Supercomputing Center in Germany, and the Institute for Computational and Data Science at Pennsylvania State University. Their findings, reported in the Astrophysical Journal, show that neutron star merger remnants consist of a central object endowed with most of the mass of the system, surrounded by a ring of hot matter in fast rotation that contains a small fraction of the mass but a large fraction of the angular momentum. Unlike most stars, the inner remnant has a higher temperature on its surface than in its core. So, convective plumes aren't expected to form as the remnant cools down through the emission of neutrinos. Now, this new research is really only a starting point, trying to identify some of the astronomical signals likely to occur when such a merger happens. In the long run, it could help answer some really key questions about neutron stars and about the formation of black holes. This is SpaceTime. And time now to have another brief look at some of the other stories making news in science this week with the Science Report. A new study claims thinking too hard can be unpleasant. A report in the journal Psychological Bulletin looked at the level of irritation and frustration participants from different countries and professional groups experienced when undertaking a range of cognitive tasks. The authors also investigated previous studies in which healthcare professionals, military personnel, office staff, and amateur athletes were all assigned various tasks, such as testing new equipment. They found that even when people volunteer to do brain work, they experience the mental burden as unpleasant. They say in all the cases they examined, mental effort really did appear to trigger negative feelings, and they say those findings were really quite striking. So I guess when people say their brain hurts, they really mean it. Here's a question for you. Just how clean is your microwave oven? Most people think that its operations zap and kill microbes by boiling the water in their cells. After all, that's how microwave ovens work. But it turns out that's not the case. Researchers swabbed the interiors of 30 different microwave ovens, from household kitchens, offices, cafeterias, even a microbiology lab, in order to uncover the diversity of bacteria living within the microwave oven. Their report, published in the journal Frontiers of Microbiology, identified a range of microbes in household microwave ovens which actually resemble those found on a typical kitchen surface. And while some species may pose a risk to human health, the authors say it's probably no greater a risk than other common kitchen surfaces. Now, interestingly, the microbes found in microwave ovens were also very similar to those found on solar panels. And the authors say this could be because the heat and solar radiation on solar panels may have favoured some highly resistant microbe species in the same manner as in microwave ovens. Now, the authors recommend regularly disinfecting your microwave ovens with either a diluted bleach solution or a commercially available disinfectant spray. A new Canadian study has gone against earlier research showing that you really shouldn't trust ChatGPT to answer your medical questions. A report in the journal PLOS ONE asked the AI to answer 150 Medscape case challenges, a series of diagnostic problems for doctors, and found he was only able to answer just shy of half of them correctly. Also, ChatGPT wasn't very sensitive in its answers, and it was overly complicated in half its responses. Finally, it only provided complete and relevant answers in just over half the time. Now, when you think about it, that means ChatGPT is really no more reliable, maybe even a lot less, than Dr. Google. And we all know how bad that is, or at least if you're listening to this show, you should. Well, it's a case of deja vu all over again. Just a week after Apple released its last software update, it's released another one, this time due to growing security concerns. With all the details, once again, we're joined by technology editor Alex Zaharov-Reutt from TechAdvice.life.
Apple has launched new updates for its iPhone, iPad, and Mac, and it's basically more security vulnerability updates. So if you've got any Apple device, just go and check. I did check for my watch, didn't see the updates there, but this is updated very quickly after last week's 17.6. So clearly these are bugs that Apple is worried enough about to try and fix as quickly as they can. But really the big news of this week is the new Google phones. And they're launched Wednesday, August 13 in Australia at 3 a.m. in the morning. And this is the Google Pixel 9. Yeah, well, there you go. So the Google Pixel 9, but they've got the new 9 Pro and the 9 Pro XL. The Pro phone in two sizes. They've got the smaller phone, which is the cheaper one with only 2 cameras rather than the 3 cameras of the Pro models. And for those who wanted that Pro phone, but in a smaller size, they've now got that. Now, of course, better cameras, nicer screen, more durable, longer battery life, all those sorts of things. But what they have is Gemini AI infused into the device. So one of the things we saw with OpenAI was the ability to have this sort of conversation. But you need to have the ChatGPT app on your phone. It doesn't dig deeply into the rest of the phone's operating system to know about your calendar and your emails and other things you're doing. And Google has done this first to have this conversational, much more advanced artificial intelligence than the Google Assistant, the Siri, and the Amazon Alexa. So they beat Apple to the punch, they beat Samsung to the punch, and they have image generation. You can do photorealistic images. It's 3 styles of pictures that are drawn, or sort of like anime style. And look, there's a number of other cool features. All the email summarization, all of the transcriptions and various things with emails that you can do, you won't need a subscription for. But some of the more advanced features, you will need Gemini Advanced. You do have the 7 years of operating system updates and 7 years of security updates. But often the best features are saved for the new phone first, and then they'll come out a few months later. We also had new Google Buds Pro 2, which analyze the sound 3 million times per second to give you better noise cancellation. You can actually twist the earbud in your ear to make it fit in a better way whilst you're running, for example. I mean, you can sort of loosen it a little bit if you don't quite need that stronger fit so the buds don't fall out of your ears. You've got the Pixel Watch version 3 in 41 and a new 45 millimeter size, so they finally have the larger watch. They don't have a rugged one yet, like Samsung does with its Watch Ultra or, of course, Apple's Watch Ultra, but they do have the bigger sizes, which some people will like, and, faster charging times and all the rest.
That's Alex Zaharov-Reutt from TechAdvice.life. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.